We want to look at tables of data, how we graph data from tables, and also how we linearize data. Now, just a quick idea of why we might want to linearize data. If we have data that gives us a graph that looks like this, let's say, it's hard to determine exactly what function fits that data. On the other hand, if we have a straight line, it's real easy to determine the function. If it's a straight line, it's a linear function. That means it's a y equals mx plus b. All we have to do to specify the function is observe the slope m and the y-intercept b. Once we determine m and b, we have our function. Now, unfortunately, most of the things that we end up observing have graphs that have curvature. There's a concavity. And it's real difficult to tell exactly what the function that fits that data ought to be. But many times we can linearize the data. We can transform the data so that it becomes a linear function. We can fit the linear function to that data. And then we can reverse the transformation to find out what function actually fits the data. I'll start just by looking at how we do a table of data. Okay? A table of Q versus T. What do we mean by that? If I tell you to do a table and a graph of the temperature of a substance versus clock time, how are you going to set up the table? Well, Q versus T, it might seem that Q ought to be in the first column and T in the second. And that's not the way it is. T is your independent variable. Q is a variable that depends on T. We list the independent variable first. When we do Q versus T, we're implicitly treating T as the independent variable, and the independent variable will be listed first. So the order we write them in when we have the versus is not the order we write them in when we write the table. So we have Q here versus T here. Now let's just take an example. Let's say we have Q versus T data as shown here. For T equals 0.2468, Q equals 0.4, 1.6, 3.6, and 6.4. Well, as you know, I'm sure it's fairly easy to graph a table of data. We set up a set of coordinate axes, T going this way, Q going this way. And our Q versus T has Q on the vertical, T on the horizontal. Just like Y versus X would have Y here and X here. Okay? So again, the dependent variable goes here, the independent variable goes here. If we graph the data on this table, we see that we have this upward curvature. And the coordinates ought to be obvious. We've marked the scale here. The Q coordinates go from 0 to 6.4, T coordinates from 0 to 8. The graph probably isn't sketched all that accurately, so don't hold us to unreasonable standards of precision here. But this is essentially what the graph looks like. Now what we want to do is we want to think about how we might figure out what function describes Q as a function of T. If we could write down a rule like Q equals the cube root of 7T, or Q equals the cosine of 5T, or Q equals 2 to the 0.08T, some rule, some algebraic expression that describes the function. So, to linearize Q versus T, what we do is we write down our Q versus T table, and then we make some kind of an attempt to linearize. Now, in this case, for this first example, all we're going to do is we're going to square Q, and we're going to take the square root of Q. It's not unusual for either the squaring or the square root function to linearize an important set of data. Now, that's something you wouldn't know unless you've done this sort of thing, but I'll simply tell you that that's a very common way to start. And there are a lot of other tricks that you'll see when they become important, but this should illustrate the whole procedure. So if we square our values of q, the square of 0.4 is 0.16, 1.6 squared is 2.56, and so forth. We just take the numbers in the q table and we square them. And then over here we take the numbers in the q table and we take their square roots. Okay? Now I won't swear that I've got the square roots right. Actually, I think that one ought to be 0.63. I think the others are pretty nearly accurate. If I was to graph now q squared versus t, would I get a straight line graph? Well, let's take a look at, first of all, let's just notice the t values in this table happen to be equally spaced. The q squared values are nowhere near equally spaced. This is not a good indication if we were looking for a linear graph. And of course, if we actually graph q squared versus t, we see that the graph points curve upward like this. We have a point here, 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 and here, and it's nowhere near linear. So we cross our fingers and hope that square root of q versus t will be pretty close to linear. Now we see that square root of q goes from 0 to 0.64. That's a change of 0.64. Then 0.63 from here to here. From here to here is 0.62, and from here to here is 0.64. Those numbers, those changes between the square root of q values are pretty consistent, which is a good thing because the t values are equally spaced, and if these are pretty equally spaced, that means we've done a pretty good job of linearizing. Now, if the t values weren't linearly spaced, we wouldn't really be able to tell by looking at these differences. We would simply have to do the graph, and in general we do that anyhow. So let's take a look at the graph. Now we're going to zoom in on this graph just a little bit. Okay, all we've done here is to plot the approximate graph points. Again, this graph is a freehand graph. It's not all that accurate. But the graph we have is the square root of q versus t. And once we make that graph, we see that there's a nice straight line that seems to fit those data points pretty well. In general, the data points won't fit as well as what we see here, but they will often fit quite well. And we draw the best straight line we can. Once we get a straight line, we're almost home free. To determine the equation of the straight line, we take 2 points on that line. Now, we don't take 2 data points because, in general, our data has little errors, and we don't want to follow the errors around. We want to take points on the line that we think represents what the data really wants to do. So we use the dotted line here, the dotted black line, not the data points. We take 2 points on that line, pretty far apart so we can measure accurately. And we measure the rise and we measure the run between those points. Now we know that slope is rise divided by run. If our estimate is a rise of 2.4 and a run of 8, then we're going to have a slope of 2.4 divided by 8, or 0.3. The y-intercept of this line is 0, which gives us what we call a proportionality. And that's always something that we like to see. A direct proportionality of this nature usually tells us something pretty good about our function. So that at this point we have the square root of q versus t is linear. The slope is about 0.3 and the y-intercept is 0. Now, a linear function with a y-intercept of 0 and a slope of 0.3 is 0.3t plus 0. Remember, y equals mx plus b, or mt plus b. There's your m, there's your b. And it's a square root of q that equals that because on our graph, we graphed the square root of q versus t, and that's where we got the straight line. Now, if the square root of q equals 0.3t plus 0, which is just 0.3t, then if we square both sides, we see that q equals the square of, that says 0.6t squared, and that should be 0.3t squared, which is 0.09t squared. We'll continue this analysis in the next clip.